This video is about permutation tests, part of my series on randomization tests. Permutation tests are almost randomization tests, but not quite. And that not quite makes a big difference. Here's the setup for a permutation test. Consider a match pair design leading up to a randomization test. Participants are matched based on extraneous variables. One participant in each match pair receives a treatment. Different scores are calculated for each pair. That is, you take the score of the participant that received the treatment and subtract from that participant's score the score of the participant who was in the control condition. That provides you a difference score, and we're interested in testing the null hypothesis that the median difference is equal to 0, hoping we'll reject this hypothesis and find that the treatment made a difference. There is an important difference in this setup from the one that we used in the randomization test. Members of pairs were not randomized to conditions. When you conduct a statistical analysis and use functions in your statistical software, those functions have no idea of knowing how you design the study. The fact that we use this design still yields a set of different scores that we can analyze. We can still use the methods of a randomization test, but now it becomes a permutation test. Let's consider some potential scenarios in which we would not randomize to conditions. Perhaps we're still interested in the effect of a treatment, yet we cannot randomize due to ethical or logistical considerations. Consider a medical study in which a rather aggressive treatment is going to be studied. Perhaps we can find plenty of participants who are willing to be in the control group, but it's much more difficult finding participants who are willing to be in the treatment condition. So it is not a problem to take those particular individuals and find a good match in the control condition, but we can't ethically randomize to conditions. We're going to have to use those participants who agreed not only to be in the study, but also to receive the treatment. Another scenario might be that we have matched pairs and we're going to administer a treatment over a long period of time, perhaps every day or every week, maybe even for months. That may very well lead to a situation in which we can only find one member of each pair who is available for the period of time and frequency of our study. And then what about the very common situation in which we want to compare individuals on something that is pre-existing? For example, suppose we want to compare smokers to non-smokers, or suppose we want to compare students, some of whom were provided instruction using one method, others who were provided instruction using another method, but the instruction is already a thing of the past. We want to know which method yielded the highest outcome, but as researchers, we cannot conduct the experiment, but rather we're analyzing data from individuals who have already been, as it were, in a treatment and control condition, and this is now a thing of the past. Or maybe we're interested in a single population that is not a population of different scores. That is, we want to make inferences about center to a population based upon sample observations, and it's not even a match pair design. Again, when we analyze a single sample of observations, the statistical software does not know where those observations came from. They might be different scores, or they might just be scores, observations from a single population. In all of these situations, we're not randomizing, but we can still permute the plus and minus signs, that is, look at the different patterns of plus and minus signs, just as we did when we randomized. When we conduct a randomization test, as it were, but there really was no randomization in the design, there are two big implications we need to consider. First, there is no longer a strong causal model. We're not doing an experiment. And so the Rubin causal model, for which randomization is one of the key elements, does not apply. This does nothing to our statistical analysis, but it does a whole lot to the interpretations that we can make from that analysis. We can no longer make strong statements like the treatment increased the median by 2 points. Instead, we must qualify all our conclusions by noting that we are seeing potential causes, not by concluding that there is a cause. That's big. But as I discussed, Sometimes we just cannot do that experiment. And then there's a statistical implication. In order to meet the conditions for valid inference, we must now say something about the shape of the distribution of scores, be they matched pair difference scores or scores from a single sample. And that is that the distribution must be symmetrical if we want to test the median using either the original scores or ordered replacements for those scores. Notice the sign test is not involved here. We're only talking about those randomization tests in which we have scores or ordered replacements for those scores. This might seem to you like a strong condition, and indeed it is, but I will quickly point out that it is not as strong a condition as that for the parametric counterpart, which says not only that the distribution must be symmetrical, but it must be a symmetrical distribution of a particular form, namely a normal distribution. Let me take a moment to show you why the distribution must be symmetrical. Here is a picture of a population distribution of different scores, and we're going to tackle a null hypothesis that the median of this distribution is 0. Consider the lower horizontal axis as a number line. Notice that the negative numbers stop much sooner than do the positive numbers. That is, when we take the absolute value of the scores, the sum of the positive scores is prone to be larger than the sum of the absolute value of the negative scores. Well, whenever we use original scores or replacement scores such as ranks or normal scores, we take the sum of the positive scores. And if the sum of the positive scores tends to be larger, even when the null hypothesis is true, that means we're going to be prone to rejecting the null hypothesis more often than we should. This distribution has to be symmetrical so that under the null hypothesis, not only is it equally likely to get positive signs as it is to get negative signs, but it's equally likely to get positive values that are of the same magnitude as the negative values. And when the distribution is not symmetrical, that's not true. You can also see here why the sign test still works. The sign test does not take into account the magnitude of the scores. All we need is to have an equal number of positive and negative scores, and as long as the median is 0, we do. So the sign test will maintain our type 1 error rate under the null hypothesis. Any test that involves the quantity of scores will not. Now, if I pause a moment and let you think about this, I bet a question's going to occur to you, and that is, why am I bringing this up now for the permutation test? Why didn't I discuss this in my earlier videos on randomization test? Here's why. When participants within match pairs are randomized to conditions, under the null hypothesis of a median difference of 0, the distribution of differences is symmetrical. In other words, if you randomize, you're going to end up with a symmetrical distribution of difference scores when the null hypothesis is true, and that's when we need symmetry. So I didn't bring it up until now because randomization took care of the symmetry for us. Was symmetry always a condition? Yes, it was. But it was implicit that we would obtain symmetry when we randomized. Now, even in the case in which we cannot randomize, there is one way in which we can save ourselves from the symmetry requirement. Suppose that we know that the median of differences equals 0. That is, we know that there is no treatment effect. A randomization test of a null hypothesis that the median equals 0, again, consider that we know this, is a test to determine if the population distribution is symmetrical about 0. We have swapped our condition for valid inference with the null hypothesis. Here we say if we know that the median of different scores equals 0, but we test for the median of the different scores to be equal to 0, we're actually testing to see if the distribution is symmetrical. Is that very useful? Probably not. But it leads to a method that is useful. Let me show you a strange-looking null and alternative hypothesis. It's not going to feel that strange if I tell you what it is in words. The null hypothesis states that if you were to randomly pick a score from a distribution and look at the absolute value of that score, and then look at the sign The probability that that would be a positive sign is less than the probability that that would be a negative sign. The alternative hypothesis says just the opposite. If you randomly pick a score from a distribution and look at the absolute value of that score, the probability that the sign associated with that score is positive is greater than the probability that it is negative. And this is true no matter what the score is. In other words, the alternative hypothesis states that the distribution is what we call stochastically larger after the treatment. Once we have provided a treatment, scores tend to move up. If you think about what we want to know when we provide a treatment, it is that the participants in the treatment condition improved. And this says that the probability that we will find a participant at a certain value who improved is greater than the probability that we'll find a member of the control condition that improved. This is like when we were doing a test of proportion, and what we were interested in is seeing if the majority of our participants improved. The difference here is that we're not looking at whether the majority of the participants improved, but rather we're looking quantitatively to see if scores tend to shift upward. That is, to see if individuals in the treatment condition are likely to end up with higher scores than those in the control condition, when higher scores are a good thing. So when you are conducting a permutation test because you cannot randomize, you can either assume a symmetrical distribution. Again, you don't have to assume a normal distribution, just a symmetrical distribution. Or you can even dispense with that condition for valid inference and look to see if scores in the treatment condition tend to be higher than those in the control condition.